Okay, so we'll kind of leave or pick up where we left off in the slides here. So we're thinking about including squared terms, but before we jump into material, I just want to mention after class. So if you look at Canvas, I've kind of got all these materials up here. So these are the practice exams. If you come down here, I have a different category where I've uploaded, or I've not uploaded, but you can kind of see what your pre-exam assessment points were, what your take-home portion score was, what your in-class portion points were, and then added those up and kind of made it out of 100. Okay. Now, this midterm exam, I think I mentioned last class, I was going to add 2 points based off of some late add or some late drops. Looking at that average, I ended up kind of adding 3.5 points to that exam. So it was curved a little bit more than I had mentioned on Tuesday's class, which I don't think anyone will be too upset by. So you can kind of see what your total grade is in the class. Now under the assignments tab, when it shows you your grades, I kind of currently have it so that it's taking the weight of both the midterm and the final. Kind of give you an idea, if you do just as well in the final as you do in the midterm, the current grade you see on Canvas is what you would get. Okay. I'll hand those back at the end of class. There's not a whole lot of people here, so I should be able to get them out pretty quickly. Maybe I'll end class a little bit early. So if you need to get to your next class, we'll kind of get those handed back at the end. Okay. Other than that, I will also at some point tomorrow get up the next problem set. I am not expecting that you work on it at all over spring break, but just in case you wanted to, I'll get that up early. We'll probably have covered most of the material on it after today's class. It'll probably have a little bit of spillover into that class after spring break. So we'll kind of finish up on that Tuesday. I won't have it set to be due until that following Tuesday. All right. So you'll have some basically a little more in a week, even if you don't start working on it until after spring break. But it'll be related to anything that we covered from last Tuesday's class. Okay. Once again, after today, you probably could get through about 90% of it. But I just want to kind of make you aware. You'll see that pop up tomorrow. I also put up, and this won't pop up until, so where we see this here. I put up some practice questions thinking about the next quiz. So once again, I don't think we'll quite have covered everything until after the next class, after spring break on that Tuesday. So that quiz will kind of have that same due date as the problem set. It'll be due kind of that one I'll have at the end of the day, Monday, before Tuesday's class, and the problem set will be due at the end of the day, Tuesday. Right? So a little bit more time for that problem set. The quiz shouldn't be too bad. Once again, if you want to over break, you can kind of start to look at these problems, but we'll revisit some of these topics of that Tuesday after spring break so we get kind of a refresher if you want to hold off on taking it until after that. Okay. Any other questions from me before we dive into material here today?
The practices on this lockdown thing for some people, as we showed you, it did not open. So it says that it's worth 1 point.
What did I say back when I told you about this? Was that worth any, or sorry, where is it at? Was that worth any points? No, it was just, I had to assign points to it so you could actually access it and look at the question. This is just kind of a way to make sure that that respondus was working before you started the actual midterm. Yeah. It's not being factored into your grades at all. If you go into the assignments tab, it's under a category that has 0%. Okay. Any other questions before we get started here? Okay. So we left off kind of thinking about adding in squared terms or adding in cube terms to kind of capture the fact that some relationships might not be linear. Okay? And so we said we can kind of look at these squared terms. I said you could create the variable, or you could use this syntax where essentially it took the variable that you wanted to include a squared term of, and this is really what the squared term is. Looks kind of goofy, which is honestly why in practice, I typically actually create the variable myself, just so it's a little bit easier to kind of read in the output. But either way, it should give us the same results. Okay. We then kind of said, okay, I can look at the statistical significance of either the linear or the squared term. We also said we could calculate marginal effects. So we said, where did this marginal effect come from? I think at the very end of class, I kind of showed you, you can calculate it in Stata. I wouldn't expect you to like plot it, and I kind of showed you how you could do that in Stata. But the marginal effect is essentially, if I take a derivative of this equation in respect to the variable that I'm interested in the marginal effect of, that should tell me the marginal effect. When everything was linear, if I have y is equal to mx plus b, when I take a derivative of that, all I'm left with is b. Essentially, our coefficient was our marginal effect before. Now, when I've got a squared term, I need some light here because I can hardly see what I'm doing. So now if I take a derivative of y in respect to this x1 variable, I'll have not only beta 1, but 2 times beta 2 times the value of that variable. So my marginal effect will depend on the value of that variable. This is most things we have in economics. As I invest more into capital, initially, I'm going to get really large changes in the output per worker. As I invest more and more, spending money on things that don't matter as much, that marginal increase in output is going to get smaller and smaller. We likely have marginal effects that the same $100 invested is going to have a very different marginal effect on my y variable at different levels of capital or different values for x. Okay, so our marginal effect will depend on that value of x. We kind of said we could think about the number of COVID cases here. If I go back and look at these coefficients, here was my coefficient on the linear term. Here's my coefficient on the square term. That was my beta 1 and beta 2 values. All right, so I'm going to use those to calculate marginal effects for different hypothetical values for x. Okay? So if I use those values and I wanted to say, okay, what's the predicted change in the number of COVID cases if the population of, say, Bloomington increases? And I think here, instead of 1 person, we had it scaled to represent 10,000 people. This is kind of the example we left off on. So here, my marginal effect would be that coefficient on the linear term plus 2 times that coefficient on the square term times whatever this hypothetical x value is I want to make the predictions for. So for us, flies down. So for us, this is going to be Bloomington at 80,000 people. That would be represented by a population value of 8, right? Representing 10,000 for each unit, so 80,000 people. So if we have 10,000 additional people in Bloomington, the number of COVID cases went up by about 1,200. Now, we kind of said the fact that we have this squared relationship, that marginal effect is going to vary for different values of x or different populations. So if I looked at Indianapolis, right, if I see if they have a population of 2 million, and this is like getting rid of kind of the outskirts or the metro, for them, that value of population or x would be 200. I'm using the same coefficient on the linear term, same coefficient on my squared term, but now I'm making a prediction for the marginal effect of a city of not 80,000, but of 2 million. So you can kind of see here, now if I have a 1 unit change or 10,000 additional people, now the effect is a little bit larger. Right? This is the idea that more people in larger areas, they're interacting with more people. You kind of think about, you can even dive into network theory. This is going to mean the same 1 person in a large city is going to have a much larger effect than 1 person in a small city, at least here in terms of the number of COVID cases. Okay. So this was kind of the idea of using that marginal effect. We could make predictions at different hypothetical x values. Okay. Now, we're also going to look at, so I said you could do this in Stata, but we're also going to talk about this in a slightly different context, and then I'll kind of show you some examples in Stata with this, how we would actually come up with these marginal effect values, not by hand, but in Stata. Okay. So I had this idea. This is a project I'm kind of still currently working on, but I've had some other papers I've gotten out there. So there's this Yerkes-Dobson theory, which says, and this could apply to studying for an exam, right? As I first start studying for an exam, those first few hours, has an increase in my performance, right? But over time, right, maybe that starts to decrease, okay? What could be true as well is if I made your exam worth 1% of your overall grade, how much are you going to study for it? Not a whole lot, right? But as I increase the percent that it carries, what are you going to start to do? So if instead of 1%, it's going to be 20% of your overall grade, you're going to start to study more, or the predicted hours you study is going to increase as the weight of that exam increases. Now, if I keep on increasing that, so if you study more, you should see an improvement in your performance, right? If at a certain point I make it worth 100% of your grade, what are you doing? Yes, you're studying a lot, but you're really stressed out, right? So as I initially start to increase the incentive of this task, right, studying to perform well, initially increasing that percentage is going to cause you to increase your performance. You're putting more time into this task, right? You're learning more of the material. You're going to start to perform better on that exam. But there's a certain point where the weight gets so high, you're so stressed out, you start studying things that don't even matter. You're getting in your own head. You're triple check, you're not thinking straight. So as I increase it to a certain point, maybe my performance actually starts to go down, right? So this is the idea that when there's a pressure situation, initially, or you're giving out incentives, initially it could increase performance. But eventually gets to a point where it's so much added stress to an individual, they actually start to perform worse, right? So I took this kind of in the context of a basketball shot, right? So here I'm trying to predict whether or not somebody makes a free throw, right? They're at the free throw line. I watched IU last night, unfortunately. But right, if I'm taking a free throw shot and the score differential of the game is really large, right? My team's up by 30. How much do you think I'm focusing on this task? Probably not a whole lot, right? As the game gets closer and closer, well, we're only down by 5. I want to make sure I make this so the game, I might focus a lot more on this task and my performance would increase. But if it's a tie game, right? Now I'm like, oh, if I miss it, or sorry, I'm down by 1. I miss it, we're still down. If I make it, now we're tied. So there's so much pressure on this task, I overthink it and I actually start to perform worse. So maybe this score differential, right, has a nonlinear effect, okay? So I went ahead and ran this regression. And we'll get rid of Zoom's thing here. I am recording this, right? Yes, okay. So this was kind of this Yerkes-Dobson theory, is this idea of pressure, right? So I look at my coefficients. Sure enough, the linear term is positive, but that squared term is negative. So as kind of the pressure of the shot increases, initially my performance goes up, but then at a certain point, it's going up at a decreasing rate. Potentially, it starts to go back down. So this WPA measure, it's kind of like that score differential, but it captures a lot of other things. Captures the score difference of the game, how much time is left, right? I think it had some other things like whether or not, it's a tournament game versus not. So it's kind of just somehow capturing the pressure of the shot, okay? So if I had kind of a positive effect, right, or a positive coefficient on my linear term, but my squared term had a negative coefficient. So I was thinking about kind of this pressure measure was the variable that was my independent variable, was the thing that was changing. And then kind of whether or not I made this free throw was the variable I was trying to predict. So initially, as that WPA variable increases, I'm going to see that the free throw being made increases, but at a decreasing rate. Now, if I keep going, what's eventually going to happen to this equation? Well, if I have a squared term, there's eventually going to be a point where it starts to decrease, right? So I can think about, we're going to call this kind of our turning point of that marginal effect. So if I was thinking about the turning point of any marginal effect for any X and Y value, so let's say I have any X variable, but I've included this square term. We said our marginal effect, or the change in Y over the change in X, would be beta 1 plus 2 times beta 2 times what? X. If I want to know where does this marginal effect go from being positive to negative, what am I really looking for? Where does this marginal effect equal 0? Right? Where does it kind of switch? Okay. If I am solving for what value of X do I see this turning point exist, it's just a little bit of algebra. I subtract beta 1 from both sides. I divide both sides by 2 times beta 2. And I get that this turning point, or the value of X, where the marginal effect goes from positive to negative, is going to be negative, whatever the coefficient on the linear term was, divided by 2 times that coefficient on the square term. Okay? So I can find, this is important if we're thinking about different things, maybe that, effective population, maybe there's a certain point where having more people, maybe it actually, I don't know, somehow decreases the number of COVID cases. That one, it doesn't really make a whole lot of sense. But in this case, there's going to be a point where I see the effect go from being positive to negative, right? The slope is positive here. Eventually, it becomes negative. The slope represents my marginal effect. So we can calculate this because we have the coefficient beta 1 on the linear term, and we have the coefficient on the squared term. Right? So all we would be doing here kind of, oh, my slide's a little bit off here. Must have a different version because I was looking right here. All right. So it looks like that kind of squared term doesn't have a statistically significant relationship. So before we even think about turning points, does this squared term actually matter? Not at any statistically significant levels. Okay. But maybe I had an important omitted variable. We said, if I have an important omitted variable, it could influence my coefficient on the linear term, but it also could influence the coefficient on my squared term. And maybe that bias in each of those is different, right? Because if I'm thinking about it, it would be whatever the coefficient of the omitted variable was times the covariance of that variable that I omitted with the variable I included, but divided by the variance on the included variable. Well, that variance on the included variable, when it's linear, would just be the variance in x1, but it'd be the variance in x1 squared for that coefficient on the squared term. So it might impact those estimates differently. So here was our kind of original p-values. If I instead add in, so I didn't have game seconds in the previous regression, so maybe this measure of pressure, it matters more at the end of the game, so I'm now controlling for that, right? Well, now what do I see? Oops. My statistical significance, it's now no longer not statistically significant, it's statistically significant at really high levels. So we can still suffer from the omitted variable bias in the context of our squared terms coefficient can suffer from it, okay? Excuse me. So now that we're here, let's start to think about calculating these marginal effects, right? We have a statistically significant squared term. I want to start making predictions for that marginal effect that WPA or this pressure measure has on whether or not they performed well this task, that free throw being made, okay? So I can plot this out in Stata. I kind of showed you the code to do this last class, but it looks like my what? So WPA is some measure of pressure. Initially, the marginal effect of this pressure is positive. Players start focusing more on the task, they perform better. Looks like it starts to become negative at about what? 0.05, if I'm just kind of roughly looking at this here. And then anything after that, the pressure is so great, they actually start to perform worse. Okay? So I kind of said, how can we find that marginal effect? Well, once we find the marginal effect, set it equal to 0, it's really just kind of a little bit of algebra to solve for that x value where that kind of marginal effect goes from positive to negative. Okay? So we can find this, right? So we'll take a look at Stata, and I'll show you some ways to do this. So we don't have to do it by hand. We could. We can also code it up. So I saved some of the edits that we made last class. I'll upload this do file after today's class, where it includes any edits that I made during class. So we did all this stuff last class. We'll scroll down here. I want to look at this small free throw data. Okay. So I'm going to make sure, I think I've got my global set correctly. Yes, I do. I'm going to open up that small free throw data, which is kind of one of the files that I uploaded. You can kind of find it on the home page or under the files tab. So we're going to open that up and think about, I'm going to run this code. This is rename some of the variables and kind of create some dummies that we can include. Okay, it's taking a little bit of time there. So I'm going to run this regression where I've included both the linear and squared term. I'm kind of using the shortcut, right? You could always create that WPA squared variable yourself. In fact, I'll do that later on to show you something that might be a little more helpful, okay? So I'm going to run this code so that we have that last regression that we were just looking at in the slides, right? Same coefficient values, both highly statistically significant, okay? I could run some of this code and plot them, right? And that's kind of that visual I was showing you. If instead I was just interested in the specific marginal effect of two different WPA values, okay? So I'm going to run my regression. If I use this shortcut, when I use the margins command, it'll look at that marginal effect, take the derivative in respect to WPA, and return to me all of the predicted marginal effects from 0 to 0.1. And then this is the jumps that I wanted to do. So instead of going up by 0.01, I just had 0.05 here, so it doesn't show us as many values. Okay? So I'm going to run that margins command. We're waiting here. And it basically tells me, okay, at that pressure of 0, here's the marginal effect of a 1 unit increase in that pressure variable. If I then go to 0.05, here's the marginal effect of a 1 unit increase in that pressure variable. et cetera, et cetera. So it's kind of not great because it like shows me these numbers. Well, I'd have to remember that those numbers represent the predicted marginal effect at 0, 0.05, 0.1, 0.15, and then 0.2, right? 0.2 is kind of where it stops. If I wanted to, I can make it stop at 1, and that's fine. It's just going to give me, we'll wait here, marginal effects not just at these 5 different x values, but at a lot more, right? So this is going to be the one that we want to focus on here. I'm going to compare to it and show you what I think is probably an easier way. So I'm just going to rerun this code in the background so we have kind of that simplified version of it. So instead of using this margins command, typically like if you're getting to the final exam, you're going to have to do this by hand, right? So it's probably better to think about what that's going to look like and look at a code in Stata that looks more similar to what you're doing by hand. So anytime I wanted to do math in Stata, I said we could use this display command, okay? So if I use this display command, what's probably an easier way to keep things straight is create that squared variable for yourself. So instead of using that kind of shorthand syntax, just create that squared variable, okay? Then in my regression, I want to include the linear and the squared value of that variable, okay? So this should give me the exact same results that I found before. It's just a different way of doing it, okay? But if I then think about, I want to find these marginal effects, well, what do we say the marginal effect is? It's the coefficient on the linear term plus 2 times the coefficient on the squared term. We said, how can we grab coefficients from a regression? So I've shown you examples of this in the past when we were trying to like make predictions for y. It's just this underscore b and then whatever variable I want the coefficient of. So take that linear terms coefficient, add to it 2 times the square terms coefficient, and then multiply it by hypothetical values of x. So the 2 hypothetical values I've chosen here are 0.05 and 0.15, okay? Now, if I go back here, they should be the same as that margins command predicted. So I think this would have been what? 0, 0.05, 0.1, and 0.15. So hopefully when I do these calculations for these hypothetical x values of 0.05 and 0.15, I see the exact same values of the margins command calculated. That's what it should be doing behind the scenes. I'm just now kind of doing the math, right? Now I say doing the math, I'm having Stata do the math for me and then just displaying that value. If I was writing this out by hand, what I would do is take the coefficient on the linear term, 0.545. I would then add to it 2 times, what, negative 7.5-ish, right? That coefficient on the squared term, and then multiplying that by my hypothetical value I'm interested in finding the marginal effect of, okay? So if I run these 2 commands, sure enough, I get negative 0.2, negative 1.7, which were the exact same values I was finding using that margins command. I just think this is a little bit easier to do it this way because I'm really saying, okay, what are the values of it? It's not just telling me like at 1, 2, 3, like all these different iterations. And I can kind of grab those coefficients a little bit easier. Now, if you use the shorthand, there's still a way to grab the coefficient of the squared and linear term. It's just a little bit more complicated. I wouldn't expect you guys to know how to do it. I would kind of think about if I ask you this on the problem set, all you would have to do, you could do the work by hand or use this display command, creating that squared variable for yourself. Okay. Is that clear what I'm saying there? Any questions on that? Okay. Now, if I have the coefficient on the linear term and on the squared term, I can also calculate the turning point, right? So we said the equation for the turning point was negative, whatever that coefficient on the linear term was, divided by 2 times that coefficient on the squared term. So once I run that regression, I can find the turning point by taking that, basically have Stata do that math for me. You know, if I think about, if this is easier, -1 times, right? I have a negative sign out front. That coefficient on the linear term divided by 2 times the coefficient on the squared term, right? What this essentially will tell me is the value of this pressure variable or the effect on our y variable, or if the free throw is made, goes from being positive to negative, right? Or where the increase in pressure starts to not improve performance, but actually decrease the performance, is right around 0.03. Okay? Now, what this is, the units of WPA is a little bit weird to think about, but it's essentially like an increase in the pressure of the situation. Okay? So this would kind of be a way that we could calculate turning points as well. Okay? Any questions on that idea before we keep moving? Just to kind of give you another example here. If we went back up and I use that COVID county data, and then I kind of come down here where we left off last class. So let's say I'll run all this. This kind of gave me my marginal effect for different population values. Well, here, for this different regression, I've got kind of that coefficient on my linear term, coefficient on my squared term. Now, this is a weird one where if they're both positive, it's increasing at an increasing rate. Will I ever have a turning point? No, right? In fact, if I think about, well, technically I will, because if I take that derivative, I'd have what? Negative the linear coefficient over the squared coefficient. But for population, if these are both positive, my turning point is actually at a negative value. Can population ever be negative? No. So technically, I would always have a turning point. It's just that for the context of some examples, that turning point won't make any sense, right? So if I think about population, and I was trying to predict the number of cases, what that means is my predicted number of cases based off of population was increasing, but at an increasing rate. Well, the turning point still exists. It's just that now my turning point is going to be at some negative value. But in the context of this question, can I ever have a negative population? No. So the turning point really is not practical for us. Okay? Sometimes it will be, right? Maybe if I had slightly different values, like I would have a turning point that exists. But for this example, we wouldn't. Right? And my second, this is my second example, I guess. But my first example, right, we did, right? We actually had a WPA measure where, what do I want here? Where when we calculated that turning point, it was a positive value. WPA, we take a look at it. Well, actually here. Huh? Oh, sorry. Didn't hit this hard. There we go. So now if I'm kind of looking back here, we'll go back up to our earlier example. I had this turning point of 0.03. What's one way to maybe check? So I'll kind of go back, open this up, kind of come back down here where we calculated that turning point. We're waiting a little bit. One way to check to see if this turning point exists. Now, in our earlier example, it's pretty easy. We know population can't be a negative value. Here, if I don't really know what this WPA variable is, and I don't know the range, what's one easy way I could check it? Just summarize it real quick. And I see, oh, it is only between 0 and 0.1 in this data set. So does a turning point of 0.03 make sense? Well, is it going to be in the data? Yes. So I could actually see it occur. If the turning point was like 0.3, do I care? No, because I never see that value exist in the real world. Just like we never saw a population of negative values exist. So we can always kind of check to see, does that turning point actually have any practical application for us to see, does that value actually exist even in this variable, right? And that's as simple as kind of looking at that, using that sum command to kind of look at what the values of that variable are, okay? No, I went through this a little quick. So any questions on this before we keep moving? Okay. So this will be like the first half of that problem set. Talk through that turning point. Now, I've only talked about including square terms and cubic terms here, What we could also do is we have some relationships where we know like a turning point never really exists. That maybe there's a increasing and a decreasing rate relationship, but we know that would never become negative, right? Or would never kind of flip over. So one way we can capture that is with logarithmic specifications, right? So a logarithmic function looks something like this, right? That yes, this effect as x goes up, y is going up at a decreasing rate, but that function kind of never turns back down. Right? We don't have a turning point usually. So if that's the case, what I can do is run these different combinations of what we call linear and logarithmic models. So we'll start first with the linear log model. So they're kind of named in the same order in which we run the regression. The first word is what my y variable is in. So linear is just what we've been using up to this point, right? Just simply the values of y. But if we're running a linear log model, what we're going to do is not use the values of x, we're going to use the natural log of the values of x. Okay? So I can create a new variable where I take the natural log of x, and then those are the values I'm going to use. So when I take the natural log, it transforms these x values to have a slightly kind of different distribution. Just like when I was squaring them, and I have now some additional information. I don't have to estimate that as a linear relationship. I can estimate it as a nonlinear relationship. So don't worry about all of this, right? Because this would be kind of the math that kind of supports why the interpretation is what it is. I'm just going to want you to know what this interpretation is, okay? So if I run a linear log model, how am I going to interpret this x value? I think I have an easier way of kind of explaining it to you, right, than looking through all that math. So let's say, I think the example I've got in the Stata file we'll eventually look at is, let's say I'm using the linear term of GPA, and I want to know the relationship between that student's SAT score and GPA. I don't think it's linear. So all the models that we typically look at have been linear. We didn't do any transformations to the variables. What I could run is a linear log model where instead of using the actual values of x, I'm using their natural log. Okay? So what you can think about anytime you see this word log or you're taking the natural log, essentially, this isn't quite what it's doing, but it's like I'm turning that variable into percentages. Okay? So now the interpretation of beta 1 is no longer a 1 unit change in my SAT score. It's going to be a 1 percentage change in my x variable, or in this case, a 1 percentage change in the student's SAT score. And now the effect on y, or here the effect, our y variable was GPA. Well, if I'm going from a percentage to kind of a unit measure, I can almost think about this. I'm going from a percentage to a probability. That might be an easier way to think about it. Linear are like probabilities. Natural logs are like percentages. So if I want to go from a percentage change to a probability or a unit change, what do I need to do? Divide by 100. So the effect of a 1 percentage change in x, or my SAT score, the effect it would have on y, or my GPA, would be beta 1. But if I'm going from percentage to units, I would then need to divide by 100. All right? So now beta 1, the interpretation is a little bit more complicated, because it's not just beta 1 is the change in y. If I have a linear log model, it's beta 1 over 100 is the change we expect in y. And it's no longer a 1 unit increase in our x variable. Because we've taken that natural log, the changes in x now represent 1% changes. Okay? Any questions on this idea? Once again, all of those lines of math is basically giving us that, the mathematical support behind why this is the new interpretation. Now, it's not quite right. We're taking things in the limit, but this is how we would kind of interpret our coefficients now. Any questions on this idea? Okay. So, just to look at some examples here, right? Why might we want to use logarithmic specifications? Well, it's the same idea as why we want to use quadratic. right? Or include a square term. Maybe I think about if I've got test scores and income, maybe I think about a family or coming from a family where I'm going from, I don't know, what did I say here? Going from like 0 to 40,000. Well, that's a huge increase in my family's income. They can provide me, and I'm actually comfortable in life. I can focus on studying for school. And so maybe the increase there is relatively large. Right? So a 0 to 400, that's a huge percentage change. But that same 40,000 additional dollars, well, if my family was already making 250 and now they're making 290, I'm still living about the same lifestyle. They're still able to provide tutors or whatever it is. So that same unit change isn't going to be as large of a percentage change. Right? So by taking the natural log, I'm capturing the fact that it's not the unit change that matters, right? It's the actual percentage change that's going to matter. Okay? What's another example of this? If I'm studying for 1 to 2 hours, what's the effect of my exam score? Well, I just increased it by 100% of how much I was studying. Probably going to have a large effect. If I'm going from studying from 10 hours to 11, well, it's still 1 additional hours, but it was a much smaller percent. It's likely to have much smaller impact on my exam performance. Okay, so it's still the idea, like we were just looking at with our squared models, that the marginal effect is changing, right, as we're looking at different values for x. Our logarithmic specifications will capture that. Okay. So if I'm thinking about this, and this is where I don't expect all of you to have the same math background to remember it, but what can you not take the natural log of? It's undefined, 0. All right. So what can I not use a linear log model for? What always has 0 as one of the values? Dummy variables, right? Same kind of like with quadratic. I can't use these dummy variables. But technically, I shouldn't be using a linear log model if what? Even if it's continuous. So maybe something like age, I could do, because you can't be 0 years of age, like if I'm looking at working adults, right? So it makes sense to use like a linear log model of age with my x variable. But what if I had the number of hours studied? What could that technically be? 0, in which case I can't take the natural log. What's going to happen? It's going to drop those observations when I try to run this in Stata. Well, those are still relevant observations. It's important that people studied for 0 hours. I want to capture that. So we want to make sure that we're not using these linear log models if the x variable is, well, first of all, we can't use it if it's a dummy variable, but also if it's continuous and it could be 0, we also wouldn't want to use it. Okay? Does that make sense there? Okay. All right. Now, if the y variable has zeros, we can still use a linear log model because we're just taking the natural log of whatever x variable we're looking at. Okay. So what are some, how could we actually get this interpretation? All right. Oops, so sorry. So if I've got, I already did this, a similar example, but if I have GPA, I'm trying to predict it with someone's high school rank. We know that maybe going from the 75th to 80th percentile is not the same as going from the 90th to the 95th, right? So the same unit change is a different percentage change, and that might matter. So how would I interpret this coefficient? Well, if I've taken the natural log of this x variable, the units are now changes in the percent. So if my high school ranking goes up by 1%, the expected change in the y variable, or the person's GPA, would not be beta 1. It would be beta 1. I'm going off a percentage to a unit or percentage to a proportion. I would have to take beta 1 and divide it by 100. Right? So I need to make sure it's a 1% change, right? Taking the natural log kind of puts the units to be percentages. But if I'm going from a percent to a linear or like a probability, it's beta 1 over 100. Now, what could I compare to the regular linear models we were using to see if this new model is actually better? Well, if it's a better model, what should go up? My r squared. And in this case, have I added more variables? No. So if my r squared goes up, my adjusted r squared will also go up. So here it's easier, right? We can look at either one and it would tell us that. All right? Now we could also compare what on the linear coefficient to the nonlinear kind of natural log coefficient to see which one is more statistically significant or which one has a smaller p-value, right? And which ones can we reject at higher levels? That would be another indicator. Okay? So here, we're going to look at, oops, these actual results. So we're going to go back in this data here. I'm going to open up this GPA original data set that I've got on Canvas. Here's where I'm going to create the natural log of this high school ranking, right? So I'm going to do that. I'm then going to run my linear model, same models we've been looking at. So the interpretation here would be, if my high school ranking goes up by 1, I'm actually getting a college GPA that's lower. Well, think about why. Being ranked first in my high school, is that better than being ranked 100th? Yes, right? So it's kind of weird, but your high school ranking going down here actually means that you're smart, right? Which is why we have this negative coefficient. So you have to think kind of sometimes hard about how what these variables represent. Now, I've got an R squared of 0.11, and this is highly statistically significant. Not that much of a surprise. Your high school ranking is probably a good predictor of your first year college GPA. If I instead run the linear log model, right? First of all, how would I now interpret this variable? If my high school ranking goes up by 1%, my GPA would change by 0.19. That's a pretty large effect. But why? That's not the actual change in y. The actual change in y would be what? The coefficient divided by it, right? So the actual predicted change in my GPA would be what? Negative 0.0019, a much smaller effect. Just having one rank higher in my high school, it's going to predict my GPA is a little bit better, but not by much, or at least a small amount. Now, is this a better model? What's happened to both my R squared and my adjusted R squared? They're the exact same thing, right? They're both now higher. Okay? So this would suggest the linear log model is better capturing this relationship between these two variables. Okay? Also, what would suggest this is a better model? Well, the p-value looks like it's 0 in both cases, but what else could I compare? My test statistic. What levels can I reject at, or can I reject at higher levels when my test statistic is higher? Which of these has a higher in absolute value test statistic? The linear log model. Right? So both those things would suggest to accurately capture the relationship between high school ranking and GPA, I should be using that linear log model. Okay. Any questions before we keep moving here? So I think I'm going to stay to here. There's some stuff in the slides, but I think it's easier if we go through it here. I'm going to show you similar output. So let's instead, I had another example where we looked at a linear log model, but now let's think about instead, I'm going to scroll down a little bit. What if I want to look at, oh, here we go. I want to have a log linear model, right? So here I'm going to think about, I don't want a linear log model. I want a log linear model. So once again, when we're writing these out, the first word always refers to my y variable. The second word is my x variable. So before, with a linear log, I had the regular value of y, but the natural log of x. With a log linear, I'm taking the natural log of y using the regular values for x. So here I'm going to create that natural log of GPA, right? What I'm then going to do is run a regression where I'm looking at the college GPA as my y variable and the SAT scores as x. So I have a log linear relationship. Now, before I keep moving with this, why is there an issue running this model? I'm going to ignore it, but why could you tell me I shouldn't be using this model? What does it tell me when I created this new variable? Why did I have missing values? What must someone's GPA have been? 0, right? So we wouldn't probably have known this ahead of time, but I must have someone who just stopped showing up to class after, very early, right? So I really shouldn't be using this model, but we're going to just act like I didn't have any I didn't have any GPAs of 0 for right now. So when I'm thinking about running this model instead, everything gets kind of flipped. So if I now want a log linear model, I'm taking the natural log of y, but I'm leaving x as kind of that regular linear term. Okay. Well, now, if I think about taking the natural log, it's almost like my y variable is in terms of percentages, but my x is still in units. Okay. So how would I interpret beta 1? Well, now it's just like it was before. It's going to be a 1 unit change in x is going to cause my predicted y value to change by beta 1. But if I'm going from units or a probability to a percentage, well, if I'm converting kind of a probability to a percent, I need to do what? Not divide by 100, but multiply by 100. Okay. So now instead of dividing by 100 from a linear log model, when I have a log linear, the interpretation of beta 1 becomes a 1 unit change in x causes the predicted y value to change by beta 1 times 100%, because y is now in terms of percentages. So if we think about our example, I'm looking at GPA. I've taken the natural log, or I have a log linear relationship between that and my SAT score. So how would I interpret beta 1? It's a 1 point increase in SAT score causes my predicted GPA to change by beta 1 times 100%. Now, to get these actual values, I need to run the regression. All right, so we can kind of take a look at that now. So any questions on this idea? So it might help to write these models out and think about anytime I have a natural log, that variable I can now think about is not in units, it's in percentages. So if I go back and actually look at this log linear model and run the regression, how would I interpret this coefficient? If the SAT score of a student or individual goes up by 1 point, the predicted change in their GPA would be not 0.0007, it'd be 0.007 times 100, so 0.07. And it's not that my GPA goes up by 0.07, it goes up by 0.07%, right? When I'm looking at the natural log of a variable, everything is now in percentages. Okay. So pretty easy to run these in Stata. We just have to create the natural log variable and then run the regression. Now, I'll do one more since we're here, and I've already got these variables created. So I had a linear log. Our old models were always linear. We didn't do any transformations, and we had a log limit. What if I have a log model? All right. So if I think about, if I take the natural log of both of these variables, so we'll kind of think about in general context and then this example that we're looking at. So if I've got the natural log of GPA and I've got the natural log of this person's SAT score. Well, when we have the natural log of our X variable, it's not a 1 unit change, it's a 1% change in X is going to cause my predicted Y to change by beta 1. But if I'm going from a percentage to a percentage, do I need to do any conversion? No. So it's now a percentage change of beta 1. So if I looked at my GPA, it would be, if there's a 1% change in SAT score, it would kind of cause that predicted GPA to change by beta 1%. Or if we go to running this in Stata, we can have some actual values to this. So all I have to do, create those natural log variables, run that. Oh, did I forget to create the one earlier? I must have. So if I take the natural log of SAT here, how would I now interpret my results from a log model? If the SAT goes up by 1%, my predicted GPA goes up by 0.74%. Okay. So we can make these different interpretations. They're a little bit more difficult now, right, than they were with a linear model, right? We have to remember to make some conversions. Now, I would argue the log model is not bad because instead of units to units, it's still percent to percentage. We don't have to scale beta 1 at all. What do you think I'd want to use a log model to estimate in economics? If I want to look at a percentage change in response to another percentage change, that would be an introductory micro elasticities, right? So we can use log models to calculate elasticities. Okay? If I had price quantity data or I had quantity income data, right? Whatever elasticity we want to measure. So we see these different models used quite often. Now, if I was trying to make the choice between the three, and just so I can go back very quickly between them, I'm going to run them again. So where was I at here? So let's run the linear model, the linear log model, oh wait, was this? Yeah, this is the right one. Where's my log linear and my log, just so I can scroll back and forth between them. Well, what's happening? What's one value I could look at between all four models to tell me what is the best fit? Well, if I'm interested in this relationship between SAT scores and GPA, I want to know what variation in GPA is the best explained by my SAT score, what model. I could look at my R squared. So 0.12 from the log model. 0.1285, so slightly higher in the log linear. So right now, that's the best one. If I compare that to the linear log, 0.159, okay, now that looks like it's the best one. Comparing it to the linear model, oh, I actually have a situation here where sometimes these different specifications aren't necessarily better. In fact, in this case, what had the highest R squared? The regular linear model. That won't always be the case, but really to kind of determine what model we should be using, we can just compare those R squared values. Okay. Now I could also kind of compare that statistical significance. So 28, 27, 24, 24, sure enough, lines up with the R squared, that the one that had the highest test statistic or the highest statistical significance was that linear model. So those are kind of the two things we can compare across these models to determine which one is better. Okay. Any questions on that idea? Kind of making these model comparisons. So I think, once we go through some stuff after spring break on Tuesday, we'll still be looking at some of this linear log stuff. So we'll just get more examples and make more interpretations. Just to kind of give some full disclosure, right? We kind of went through this stuff in Stata. Now, what we didn't cover, and I'm going to hold out on actually doing this until after spring break, is we can actually take the natural log of multiple variables. So if I want to run a linear log model, I don't just have to take the natural log of one variable. I could look at the relation, take the natural log of several variables, right? I don't have to just transform one of my control variables. I can transform a lot of them. We can then start to think about, should I be running this as a linear model or a linear log? Well, if I'm doing it for multiple variables, I could essentially kind of start to run these joint hypothesis tests. Okay? We'll have a slightly different way of doing this than what we've talked about in the past, but essentially, I'm going to still have a restricted, unrestricted model, and there's going to be a way we can tell which of these we should use. So we'll kind of hold off, wait for that until after spring break. So we'll come back to these slides after spring break. We talked about log linear. We talked about log models, doing interpretations. Similar idea, and I pointed it out when we had the one problem in Stata. I can't use these logarithmic specifications if my variable that I'm taking the natural log of has a 0 value. So dummy variables, all bets are off. So what can I never use a log or a log linear model for? If my y variable is a dummy variable. So when we were trying to make like the predictions for like, was the free throw made? That was a dummy variable. Could I ever run that as a log or log linear specification? No. In which case, even if I think that there's a nonlinear relationship, if my y variable is a dummy variable, what am I forced to use? Either a linear log model, or I could include a squared or a cube term, right? But I can't use any of these log or log linear models if my y variable, my dependent variable, is a dummy variable. Any other questions on anything we've talked about up to this point? So we kind of covered this. We can kind of compare those r squared and the statistical significance. I kind of have this testing these different models for multiple variables. We'll talk about a actual, like a better test, because what I was telling you earlier isn't quite correct. Because if I compare the r squared of a linear to a log model, by taking the natural log of y, inherently, what am I going to do? I'm going to change the variation that exists in y. And so my total sum of squares is going to be different. So I shouldn't really be comparing those, right? Because I can only ever truly compare models with my r squared if they have the same y value. When I've taken the natural log of y, I can't compare that to when I have. So I just, for right now, kind of simplified it, and we could just look at the r squared. We'll talk about next week a more complicated way to do this. I shouldn't say complicated, but a better way to do this, which is we really shouldn't be comparing like linear to log models because our y variable is different. Right? And so if we ever want to compare those models, we have to run a different type of test. We can't just look at the r squared, which is called this Davidson-McKinnon. So we'll talk more about that afterwards. Right? But we got to start. We got to walk before we can run. So today we walked. When we come back from spring break Tuesday, we'll run. Okay. And then the only other thing I wanted to mention here, get done a little bit early. I have a second example. I might kind of run through that just to refresh our memory after spring break before we kind of jump into some of these more complicated logarithmic terms, or sorry, logarithmic concepts. The only other thing that I want to do today, since you're all here and you hung around instead of getting off early for spring break, I got this in-class quiz. So got it set to be due. Well, kind of cut this down. Everyone should be able to get it submitted here in the next 8 minutes for sure. Whoops. No, that's not what I wanted to do. There we go. Right. So I'll publish this. I think it's 79.02. I'll kind of check myself as we look at this here. Let me know if that gets you in. If not, anyone got that to work? No. So I must be remembering this wrong. 77.2, right? Not 79. 77.2. We'll then kind of take a look at what these questions look like. I'll kind of run through them kind of quick here, right? So this should be a pretty easy concept check. If I have exam scores and attendance and I think it's a nonlinear relationship, and I have the exam score being the dependent variable or my y variable, which of the models can I not use? Assume that the lowest exam score is above 0 and the lowest attendance score could be 0. So if I could see that someone has attended 0 classes, that's a possibility, and that's my x variable. Which model here could I not use? Log, right? Now, technically, even though I have zeros there, I can still use quadratic and cubic models if the x value is 0, because it's also other values, right? The, what did I have here? Attendance could be 1, 2, 3, 4, 5. The only time I can't use a squared or cubic model is if the only values are 0 and 1. So these squared and cubic models, I can't use them for dummy variables, but it's okay if the variable itself includes 0, right? As long as it's 0, 1, 2, 0.5, there's other values in there as well. Okay? So the only one I can't use here should be this log model, right? I can't take the natural log of that x variable. And then if I'm looking here, what would kind of suggest that I'm capturing a better relationship between the exam score and attendance? So attendance improves exam scores. I told you I'd have some regression output that shows that. So here, if I've got an r squared of 0.12 from the linear model, I've got 0.11 from kind of my squared model, and I've got 0.1287 from my linear log model. I think those are the only three. Oh, no, I've got a log, 0.132. So what has my highest R squared? Looks like it was this log model. I had the highest R squared value, right? So that log model, just based off of comparing R squared, should be the one that we use. Now, I kind of already alluded to the fact that we're going to complicate this, so this in-class quiz won't really apply once we talk about things on the Tuesday after spring break, because I really shouldn't be comparing a log model to any time where I've only used the linear term of y. The R squared is an okay measure. It's not necessarily a bad thing to use that to compare, but a more accurate way to compare is what we're going to call that Davidson-McKinnon test, and we'll talk more about that after we get back from spring break. Okay? So looking at the R squared value, that log was kind of the best model, and then we said, which of the following can I not use? Well, if the x variable could be 0, I can't take the natural log. So that log model wouldn't work. Now, I didn't have it as an option, but what other model couldn't I use there in that first question? So I can't use a log because the x variable had a 0. I also couldn't use a linear log. Okay? I didn't give you that as an option. Otherwise, there would have been multiple answers. Okay. So make sure you're getting that submitted. Like I said, I think I had it to be what, 152. So as long as you get it submitted in the next minute or two, you'll be fine. If you want your exam, I've got them. I can kind of hand those back on your way out. Otherwise, look for that problem set. If you want to get an early start, you can start reviewing like the first half of those practice problems. Have a fun, safe spring break. I want to see you guys all back here on Tuesday after we're done, after spring break's over.